Yeah.
Okay, we're right in time, so I suggest to go ahead. It is my great pleasure to announce today's last speaker, Professor Franco Fagnola from Milano, and he's going to talk about Gaussian QMS, irreducibility, and positivity properties. Please, the stage is yours.
Okay, thank you. I would like to thank, first of all, the organizers, in particular, Ivan Remizov, for inviting me to the conference. And, well, I will talk about this subject that is a work in progress, mostly with Damiano Poletti, who will give a talk on a related topic on Friday, and Juliana Gredo, who's not here for time zone reasons. Okay, and so this acronym means quantum Markov semigroups. So semigroups of completely positive identity preserving operators on well, a von Neumann algebra, essentially. Well, and this is an outline of my talk. So I will begin from the definition, I would say the standard form of the generator, because these are semigroups of operators on operators, but one can take advantage of this representation of the generator to reduce many problems to standard operators, and so one has a better intuition. And this happens also for what are Gaussian quantum Markov semigroups. I will explain why Gaussian, because they transform quantum Gaussian states into quantum Gaussian states. And then I will begin discussing the first qualitative properties that one is typically interested in for well, the description of the dynamics, which is well, represented by, which is described by these semigroups. So irreducibility, invariant density, well, positivity properties, well, and so on. Invariant densities, which is, of course, the non-commutative analog of existence of invariant densities in spaces of functions. Okay, so first of all, I recall the definition. One has a von Neumann algebra, but one can think of bounded operators on an Hilbert space for simplicity. And so a quantum Markov semigroup is a semigroup Markovian in the sense that it is identity preserving, and maps of the semigroup at any time are completely positive. This is the natural positivity property that is required when these maps act on a non-commutative algebra. And it means the following. It means that whenever you take, you consider a matrix of an n by n matrix whose entries are operators. So these are operators. So the whole is an operator on this bigger space, and you apply the semigroup, the map of the semigroup to each entry. Then if you begin from a positive operator, well, the output is again a positive operator. This is the natural positivity property when the algebra A is non-commutative. When it is commutative, it is equivalent to the usual positivity, as it is well known. But anyway, for the purposes of this talk, complete positivity in practice means that the generator has a certain special structure. Well, moreover, there are also the continuity properties, which are the natural ones for Neumann algebra, which is the dual of another Banach space. For example, if A alpha is an increasing net of operators which converges weakly, sigma weakly, or strongly, these properties are equivalent in for Neumann algebras, then also the transformed net converges in the same sense, and the time continuity is weak star continuity. As I mentioned before, one can always see the von Neumann algebra as the dual of another Banach space, and the typical example and the situation in which I am interested in the sequel is the following, in which A is a bounded operator on a certain Hilbert space, and the predual are trace class operators. Well, in this case, one can see this semigroup as the dual of another semigroup, which is a standard C0 semigroup. Okay, so I said that complete positivity implies a special structure on the generator, essentially. Well, in the case of non-continuous semigroups, namely, or uniformly continuous in another language. There is this celebrated theorem, which gives the name to the GKLS representation. So if one has a semigroup of completely positive maps on bounded operators, then the generator is represented in this form with certain operators L and H that are bounded. The number of operators L might be infinite, but this series is strongly convergent, so it on the whole space, so it converges to a bounded operator. And this theorem holds in the case of non-continuous semigroups, but it turns out that one can find many examples of non-continuous semigroups that whose generator has a similar structure, and with unbounded operators L and H, and these are this is the case of Gaussian semigroups, Gaussian quantum Markov semigroups. So this is a step towards Gaussian quantum Markov generators. Well, first of all, one can see that one can put together multiplication, operators acting on X, either on the right or on the left only. In this way, if one defines as G this operator, then one formally writes the generator in this form. And this G, in the case of bounded operator L and H, of course, generates a contraction semigroup. And this is what happens also in the case of Gaussian quantum-Markov semigroups, but G and L become unbounded. And to be more concrete, well, we will see later. One can generalize this structure of the generator to unbounded operators with this hypothesis. First of all, one assumes that G generates a C0 semigroup on the underlying Hilbert space. The operators L are less unbounded than G. They are, roughly speaking, a sort of square root of G. And one has this identity, which means that, well, which translates the requirement at a formal level, at least, that the semigroup is Markovian, so is identity preserving. So if we go back one moment to the previous slide, you see here, if I insert here the identity operator, and I want this to be preserved by the semigroup, L of identity equals to 0, well, is then translated by this formula. There is a way for constructing the semigroup from these assumptions. One has a formal generator, which is given by this quadratic form. One begins an iteration procedure from well, basically forgetting about this term with the else, and well, and in the end one gets a certain semigroup. I'll describe later the iteration procedure, which satisfies this equation, and this, as usual, when one constructs the semigroups starting from quadratic forms, there are some difficulties for the control of the domain of the generator, of the actual generator of the semigroup. Because here there is the typical problem that has been discussed by many authors, starting from Kato, Feller, when one constructs semigroups in this way. So essentially starting from this G and then going on by perturbation, that the resulting semigroup could not be identity preserving. But in good cases, it turns out to be. And this is an hint of the construction. One starts from the semigroup generated by G, and then by a perturbative iteration method, one goes on. There are also other variants of these perturbative methods, but they have always the same trouble in the end, in the proof of Markovianity, so preservation of the identity. Well, a tool well, there are tools that sufficient conditions that work anyway in the case I am interested in, that I begin to describe now. Okay, so this is, I will say what are the operators H and L that determine the generator that was written down in the previous pages. So there is, I use this representation of, I use this framework. So there is H, which is the Fock space over complex numbers, d-dimensional complex numbers. So concretely, there is a certain orthonormal basis, which is taken by products of an orthonormal basis on each coordinate. So but intuitively, on each coordinate, I have a little L2. Then there are creation and annihilation operators defined by this formula. Creation in the, for example, creation here in the jth coordinate means that I increase the level by 1, and then there is this factor. The domain is the natural one, which with this summation condition to make sure that the result of the definition still lies in the Hilbert space. And these operators satisfy the canonical commutation relation. This delta Jk is the Dirac delta. In an equivalent way, one can think of position and momentum operators by this definition. And well, this is the in an equivalent framework, absolutely equivalent, unitarily equivalent, could be considered by considering the unitary correspondence of this Hilbert space with L2 over Rn with complex values, Rd better, endowed with the Gaussian measure, with the unitary correspondence given by Hermite polynomials in n variables. These En would be Hermite polynomials in n variables. Qj becomes multiplication by xj, and pj I times the partial derivative with respect to the jth coordinate. So this is the framework. Then H is a second order polynomial in creation and annihilation, or in the multiplication and derivative framework, it would be a second order differential operator with unbounded coefficients that can grow at most as x squared when there are no derivation, or x times derivation when there's the derivation, or second derivative multiplied by a constant. And L is a first order differential operator. Moreover, to avoid redundancies in the GKLS representation of the generator, one supposes that these operators are linearly independent. And for these reasons, one cannot consider more than 2D of such operator cell, which are typically called the Krauss operator or noise operators. And of course, one wants the H to be self-adjoint, so this implies conditions on the matrices of coefficients written here. Yes. So the matrix omega must be Hermitian, and the matrix K must be symmetric, so that the operator H is at least symmetric. But then by standard results like analytic vectors and so on, one can prove that H is actually self-adjoint. Okay, with these operators, one considers, as before, quadratic forms, and one can construct the semigroup with a certain generator coinciding with this quadratic form, with the operator representing this quadratic form on a certain domain. And luckily, in this case, one can also show that it is Markovian applying this old result by Alexander Chebotaryov and myself, which is sort of non-explosion criteria for these operators, these generators that are quantum diffusions. So, and just to give idea of the content, this C plays the role of a certain Lyapunov function, an operator version of a Lyapunov function. And when one computes the quadratic form applied to this unbounded operator, which is the number operator, one has a lot of simplifications because of commutators, because the commutator of two differential operators of a certain order, say order, for example, 2 and 1 is another differential operator of order 1 because you decrease by 2. It is something well known, and then you can take advantage of this. So if you apply L to C, you have theoretically a differential operator of order 4, but you decrease by 2, so you go back to 2 and you can control with the C. But so with all this discussion, you you can construct a quantum macro semigroup. So a semigroup of completely positive identity preserving normal maps, which is continuous in the good topology on the on the space I described before. Its predual semigroup is a semigroup on trace class operators, which is a C0 semigroup, and has the property of mapping quantum Gaussian states to quantum Gaussian states. Or so this is and conversely, if one has a quantum macro semigroups on a Fock space mapping Gaussian states to Gaussian states, then it turns out to have, the generator turns out to have this structure. So this is also a sort of GKLS theorem for Gaussian quantum macro semigroups. Well, here there are some references. Okay, so now that I described the construction, I would like to address the problems related with the study of the dynamics that one considers that are motivated by mostly by problems in the theory of open quantum systems, but they have also a classical counterpart on diffusion processes. Well, indeed, I should say diffusion together with jumps, because the two types of processes coexist in this non-commutative formulation. So the analogy is the following. In the classical case, one has probability densities and bounded functions. This is the duality. And the relationship with the semigroup is given by this well-known formula. This is the probability starting from a certain point to be in a certain region after a time t. And here you see the picture is exactly the same. You just change the duality. And we want to study the properties of the dynamics. So the first step in the commutative framework is typically to find, or more than the commutative framework, in the case of Markov processes, is to find closed classes of states. And eventually reduce everything to the study of irreducible components of the dynamics. And so this, the non-commutative version begins with the study of subharmonic projections, determining regions of the space from which you cannot exit with the semigroup. So this is the definition. A projection is subharmonic if it is increasing for the semigroup. And a quantum macro semigroup is irreducible if it has no non-trivial subharmonic projection. And with a few line proof playing on positivity properties, one can all immediately see that this property, Tt of P bigger or equal than P for all times, is equivalent to say that this subalgebra is mapped onto itself, into itself, and or if you start from a certain density, so a trace class operator with support inside the projection P, then through the evolution, you go to another state at any time, still supported in P. So the support of a state is by definition the support of the density. So it is the closure of the range. The density is also positive with trace 1. The closure of the range or the orthogonal of the kernel of rho. And there is a simple way for, well, simple. There is a characterization of subharmonic projections that is available. A projection is subharmonic if and only if it determines an invariant subspace for the semigroup generated by G. So the strongly continuous contraction semigroup on the Hilbert space, which was the step 0 of the iteration. And moreover, for each noise operator, the range of the projection P intersection the domain of G, which is the generator of P, which is of course dense because of this property, because P is a reducing subspace for the semigroup generated by G. This is invariant under, well, the range of P is invariant under. And so in this way, one can always construct, well, reduce the problem of finding projections which are subharmonic, but they are defined on operators to an invariant subspace problem, which is a bit more easy to deal with. And even more, in an even more simple way, in the case of Markov, quantum Markov semigroups, there is a one-to-one correspondence between the operator cell and vectors of complex numbers. So if one, well, let me go back here. If one has an invariant subspace, one looks for an invariant subspace for G, which is a second-order differential operator, and L, which is a first-order differential operator of this special type, of course. Well, if one has many L, which are noises operators, then one is looking for an invariant subspace for many creations and annihilations, so for many multiplications by X and derivatives. And so in this sense, one can expect irreducibility. Well, this is the rough idea. So how many of such operators? Well, first of all, one is looking for invariance under L and G. So there is invariance under G and L commutator. So from the G and L, the commutator of G and L is a differential operator of order 1, or if you want, it is linear in A and A dagger. So you do not consider only vectors determined by L's, but also by commutators and iterated commutators and so on. So in other words, one has this iterated commutator condition that appears in many contexts like control theory, hypoellipticity, and so on. And in the end, well, this is the result about irreducibility, at least a sufficient condition for the moment. If one starts from a certain generator with M linearly independent noise operators, one looks for the dimension of the space generated by their vectors in C2D. Then this dimension increases as one considers iterated commutators of higher orders. But since you are in subspaces of C2D, sooner or later you have to stop, and you have to stop in at most 2D minus M steps indeed. And so as a result, one guesses that a Gaussian quantum Markov semigroup is irreducible if and only if one has this is simple linear algebraic condition. So the dimension of the space, of the linear space of coefficients of noise operators and their iterated commutators up to the order 2D minus M is maximal. Well, and indeed, we can prove that if you have this rank condition, then the Gaussian quantum Markov semigroup is irreducible. We do not know whether this is this condition is also necessary in general, but we know that it is in the special case when this set of operators is self-adjoint, in the sense that whenever you consider one, its adjoint is a linear combination of the original operators, L. And so in other words, this is the non-commutative analog of commutative situations where when you have in a Markov semigroup generator, when you have enough noise, you have irreducibility. Well, if not, you can have some parts of the phase space where the evolution acts as a pure translation, and so in this part you have not irreducibility. You do not, since time evolves only in one direction, you do not necessarily return to previously visited regions. Okay, related with this irreducibility, there is this property which is typically useful when one wants to computer study other important dynamical properties, like, for example, the behavior of relative entropy and so on. Because the quantum relative entropy is defined by a complicated formula involving logarithm of density. And the first step in the evaluation of the quantum relative entropy is to make sure that states are fully supported. Otherwise, you have problems with infinity. And in this problem, it is useful to know whether the semigroup is positivity improving or not. Namely, if you start from a certain state, well, here I have the version at the level of operator. If I start from a positive, non-zero, but not necessarily strictly positive operator, whether after some time evolution, the operator I get is strictly positive, so with only zero kernel. And playing with the duality, it is immediate to see that one can show that positivity improving either at the level of operators is equivalent to positivity improving at the level of densities, but for the pre-dual generator. Well, okay. Well, to solve this problem, well, first of all, one looks, well, here I recall the definition of support of a density. So density is a positive trace one operator. The support is closure of the range or orthogonal of the kernel. And well, one looks at the support of the initial density evolved with the action of the semigroup. And since one constructs the semigroup by the minimal semigroup method, through this iteration procedure, there is a standard way for identifying the support of the evolved state. Because the support of the evolved state is what you get from the zero iteration, then the first step of the iteration, and so on and so on. And if the operator G, which is a second order differential operator that generates a C0 semigroup in the Hilbert space, generates indeed an analytic semigroup, then one can make sense of all the operator compositions, commutators, iterated commutators, and so on, and one can characterize the support. The support is given by this apparently complicated formula, but for those who are familiar with, I think hypoellipticity is well, something not unexpected. Okay. Well, and one can prove now that if, together with irreducibility, one knows that G generates an analytic semigroup, so one can make sense of all these operator composition, because if you start from any vector in the Hilbert space, PT maps into the domain of all these operators, then it turns out that the semigroup is also positivity improved. Well, okay, I can better skip the proof, because after all, well, one can imagine how it goes through. And I move to the next problem that I have only, let me see, I have only 8 minutes as far as I see. So I would like to give a few ideas on the problem of existence of invariant densities and it's a solution that can also be addressed in this case. Again, here I am recalling the definition. Invariant just means this, that if you compute the expectation, this traces the expectation of the state at time t of any operator x, then you get well, then you get a constant. Invariant means that it is invariant for the action of the redual semigroup, of course. And there are two useful remarks that are a non-commutative analog of formulas well, of what is known in the commutative framework. So first of all, the support projection of an invariant density is subharmonic. And as a consequence, if you know irreducibility, you get also faithfulness and well, and uniqueness that I forgot to write. Okay, so we go to the problem of studying when you have invariant densities for quantum Gaussian quantum Markov semigroups. And there is an explicit formula, there is an explicit formula which gives an intuition in this case. Well, indeed, I forget to mention, but this explicit formula is well known to in the mathematical physics community, because it is the formula for the so-called quasi-free semigroups, which was indeed the starting point of another construction of the semigroup. Well, first of all, this is an explicit formula on certain operators, because as in the commutative case, when you have the explicit formula for the semigroup generated by the Laplacian on trigonometric functions, for example, on certain trigonometric functions, here you have these while operators, which are unitary, and if you define these two matrices, so Z and C, in terms of matrices V and U that were matrices of coefficients of creation and annihilations, you obtain two real linear operator on CD, or if you want again matrices on C2D. And in the end, the action of the semigroup is the following. There is a certain exponential factor here, and then the action on the operator is written in this way. You have the exponential of a matrix acting on the complex vector Z. So this suggests that if you have an invariant density, so you want the first identity to hold, so the trace of rho WZ must be time independent, and you apply the explicit formula so that you see that in the right hand side you have this integral. You note that this last factor, this trace is bounded by 1 because you have the trace of something unitary against something with unit trace. This is a real number, so it doesn't change the mode, and this is non-negative. So everything depends on what happens here. And by the way, this function is the so-called characteristic function of the quantum Gaussian state. So you guess that if this integral, if the argument of this integral is non-zero, then you decrease the value of this the mod of the value of this complex number. And indeed, this is the result. You can find an invariant density if and only if this integral is convergent, which was a condition that we saw this morning in the Beppe Laprato's talk for classical diffusions, indeed. Therefore, what happens is that invariant states exist if this matrix Z is stable, in the sense that E power SZ is integrable at infinity, and moreover, well, this is a condition, or if Z is unstable, it must be well behaved with respect to the kernel of this covariance operator C. But anyway, I realize now that perhaps I've been a bit too quick, so let me skip the one-dimensional case in which we can compute everything in terms of the parameters. So I refer to these references and work in progress for more detailed information, and in particular to Damiano's talk on Friday for well, something almost immediate. Okay, so I think my time is over, so thank you. Oops.
Thank you very much for this beautiful talk. So we have time for questions, please. So maybe to give the audience some time to think about questions. I actually have a question. namely this concept of irreducibility for
Yes.
quantum semigroups that you mentioned. So do I understand correctly if I consider the analogous concept for semigroups on L infinity? Then this is actually band irreducibility, right? So it's not ideal.
Right. If you consider the analog concept for semigroups in L infinity, it means that if you take an indicator function of some measurable set, then semigroup applied to this indicator function is bigger or equal than the indicator function. Yes, because projections in this case are exactly indicator functions.
Okay. So yeah, because band ideal irreducibility would be quite strong on an infinity. Okay, thank you. Further questions? Further questions?
Well, if there are no more questions, then I can ask my traditional question. From your particular point of view, which result is the most remarkable in all this setting?
Well, this is a good question, but and it is indeed a work in progress. Well, we dream of establishing a bridge between these irreducibility conditions, controllability conditions of certain bilinear systems, and hypoellipticity. But for the moment, we can, well, this program is complete essentially in the case of quantum macro semigroups on a one-dimensional Fock space. Well, because we have several domain problems and regularity problems that present time we are not able to fix.
So the most remarkable thing here that the research is far from ending.
Yes, yes, yes. Okay. And well, another important thing is that, for example, in quantum field theory, there's a lot of research on that. There's been a lot of research on Hamiltonians, which are quadratic in creation and annihilation operators. Well, these are the open system extension of this framework, because you have not only the Hamiltonian, which is quadratic in creation and annihilation, you have also the noise, which brings another contribution in the picture.
So I have another question. Also on irreducibility, actually, because I like the concept. So is this definition of irreducibility, is it equivalent to saying that for each positively semi-definite non-zero observable and each, let's say, each positive semi-definite trace class operator, so distributed state, which is non-zero, there exists a time such that the measurement is non-zero. So for each.
You mean, in other words, if you have this inequality not for all t positive, but from a certain time on, or not?
I'm actually asking whether you can characterize this equality in the first and the second, the definition in the first and the second line. Is it equivalent to saying that whenever you start the non-zero positive vector and you test against the non-zero positive density matrix or density operator, that you always, there is a time such that it's non-zero? Because on Banachnet, this is equivalent to irreducibility.
Yes, I think, well, I think so, but I think so, but I don't remember if I have checked it.
Okay, thank you. Further questions?